Some of the biggest ideas in technology, we're talking everything from your Netflix recommendations to the entire future of artificial intelligence. They all depend on solving a math problem that seems totally impossible. It's a problem that stumped geniuses for centuries, and its solution is, well, it's both super elegant and incredibly powerful. And it all kicks off with one simple, mind-bending question.
Right? Just think about that. You're a physicist, maybe an engineer. You've set up an equation to describe something in the real world. You do all the math, and the answer you get is infinity. What does that even mean? I mean, your system doesn't just explode. The universe doesn't crack in half. It means your math has just hit a wall, a point where it just can't describe reality anymore. And this isn't just some abstract puzzle. It was a real, practical barrier that was holding back progress for a long, long time.
Okay, here's the classic example. If you try to calculate the area under the curve of 1 over x, from -1 to +1, you run into big trouble right there at 0. See, on the right side, the area just shoots up to positive infinity. But on the left side, it plunges down toward negative infinity. So, what's the total? What's positive infinity plus negative infinity? The answer is, well, there is no answer. It's undefined. The standard rules of math just throw their hands up and walk away.
And this is exactly why we can't just leave it as undefined. In physics, this kind of force is related to a potential energy field. So if you calculate the work it takes to move a particle from point -A to point +A, the math, like we just saw, completely blows up. But our physical intuition, our gut feeling based on the conservation of energy, is just screaming that the answer has to be 0. The particle starts and ends at points with the exact same potential. No net work should have been done. So you see the conflict. Physics demands a real, finite answer, but the math is just giving us gibberish.
This is where a little bit of 19th century mathematical genius enters the story. Mathematicians, completely fed up with these paradoxes, came up with an incredibly clever workaround. It doesn't really change the rules of math, it just gives us a new and way more useful way of looking at this whole infinity problem.
It's called the Cauchy principal value. And the secret sauce, the whole key to it, is symmetry. Instead of just letting these positive and negative infinities run wild and mess everything up, the idea is that we can tame them. We can bring them under control by making them approach that troublesome spot in a perfectly balanced, symmetrical way. It's a method for finding a single, principal value in a mess that otherwise looks completely ambiguous.
So picture this. You're pinching the gap around that infinite point at 0. The trick is to make sure your thumb, coming from the left, and your index finger, coming from the right, are moving at the exact same speed. As that gap gets infinitesimally small, that little slice of positive infinity you're adding on the right is perfectly canceled out by the little slice of negative infinity you're adding on the left. And the result? 0. Exactly the answer that physics told us had to be right all along.
Now, this isn't just some random trick we picked because it worked. As the physicist Giuseppe Negro points out here, this is a form of renormalization. That's a fancy word for a procedure that systematically cleans up the part of the equation that's going haywire. He argues that by using the symmetry of the problem, it's really the only logical choice that makes any physical sense. It's not just a convenient trick, it's a seriously deep insight into how the world works.
So, great. This whole symmetry trick worked perfectly for a simple 1 over x problem. But how does this scale up? Well, it turns out that this exact same core idea is the foundation for solving much, much tougher problems. Problems that are absolutely critical to modern science and engineering.
So, let's meet the next boss level, hypersingular integrals. These are functions that blow up even more aggressively than 1 over x. Think 1 over x squared, or even nastier things. And these guys pop up everywhere, from calculating stress on an airplane wing to modeling electromagnetic fields. And just like before, they represent these points where the standard math just completely breaks down.
Visually, you can think of one of these singularities as an infinitely sharp spike or maybe a bottomless pit right in the middle of your mathematical model. It's a point of total failure where the normal rules just don't apply. Trying to solve a problem with one of these in it is like trying to draw a map of a landscape that has a giant, infinitely deep hole in it.
But look what happens when researchers apply these more advanced methods, which, by the way, are built on that same core principle of handling infinities symmetrically. That spike gets smoothed over. That hole gets filled in. What you're left with is a smooth, continuous, and most importantly, a useful solution. The infinity has been tamed. It's been brought under control.
Okay, so we've seen how this clever trick from calculus unlocked problems in physics. But it turns out this core idea of finding smart ways to manage these problem spots where the math breaks is also the key to unlocking the next generation of computing, quantum artificial intelligence.
Now to make that jump, we've got to talk about a really powerful tool called singular value decomposition, or just SVD. At its heart, SVD is a way of taking complex data, basically a big grid of numbers called a matrix, and breaking it down into its most fundamental parts. It finds the singular values, the most important bits of information, kind of like how the principal value found the one true answer for our infinite integral. It's just another brilliant way of taming a complex system to find this signal in all the noise.
And I am not kidding when I say SVD is absolutely everywhere. The reason Netflix has a spooky good idea of what movie you want to watch next? SVD. How does your phone take a massive photo and squish it down into a tiny file? Yep, SVD again. It is a true cornerstone of modern data science and machine learning.
So that brings up a really exciting question. If SVD is this powerful on the computers we have today, what could it do on a quantum computer? I mean, as the data we're working with gets unimaginably huge and complicated, we're going to need a whole new kind of algorithm, a quantum algorithm, to handle these essential jobs on a completely new generation of hardware.
And that brings us right to the cutting edge. Meet VQSVD, which stands for Variational Quantum Singular Value Decomposition. This is the direct descendant of all of these ideas we've been talking about, but it's designed specifically for the bizarre new world of quantum computing.
So what is it? Well, VQSVD is this clever hybrid algorithm that uses both quantum and classical computers working together. It's designed to perform SVD on datasets that are so ridiculously massive that no classical computer on Earth could ever hope to deal with them. And the goal? To build things like hyper-personalized recommendation engines, speed up drug discovery, and solve machine learning problems that right now are just way beyond our reach.
So there you have it. From a simple, symmetrical trick to deal with infinity back in the 1800s, we can draw a direct line to the quantum algorithms that are going to shape the 21st century. It's just an amazing reminder that sometimes the most abstract, impossible problems in math are just waiting for one clever new perspective to unlock a future we can barely even imagine. It really makes you wonder, doesn't it? What other mathematical impossibilities are we just one clever trick away from solving?